Swayam Prabha. Digital India. Educated India.
Okay, before we go to second order factors, I am just going to do another important factor which becomes very useful for engineering applications, right? Because if you recall, when we did transient response analysis, I talked to you about time delay, right? In many physical systems, we are always going to have a time delay. So what is meant by a time delay? I give an input now, the output starts increasing from 0 after a finite time interval, right, which I cannot neglect. Okay, so then there is a time delay. So for example, like I can have friction resulting in a time delay, right? So let's say I take this desk, I give a force, the desk doesn't start to move immediately, right? So I may need to overcome the static friction before the desk starts to move, right? That's a time delay. In let's say in fluid systems, sometimes I may give an input, like I will have some transmission delay before the fluid pressure starts to build up. Right, then what happens is that like we have a finite time delay and we need to incorporate that, correct? So if you recall, what was the transfer function of the time delay? Some people call it as a transport lag. So because if you look at process control and so on, they will call it as transport lag, because in process control they are interested in like some fluid systems, fertilizer plants, chemical plants and so on, right? They call it as transport lag, right? So essentially it's a time delay, right? So what is the transfer function of a time delay? E raised to the power minus Ts, right? Of course TDS or TS, right? So what did I put? TD for the time delay? T subscript D, right? So T subscript D was a time delay, right? So this is the transfer function of the time delay. How did we get it? Because if you recall, if we had a time delay, my input excitation becomes something like this, right? U of T minus TD. Then if you take the Laplace of this, what is going to happen? You are going to get U of S times e power minus TD. Yes, that's why the transfer function of the time delay is taken as e power minus TDS, right? Let's construct the Nyquist plot for this, right? So what will happen to g of j omega? Then this will become e power minus g TD omega, right? And what is this? How can I rewrite this? This is cos TD omega minus j sin TD omega, right? That's the real part and the imaginary part, correct? I'm just using the Euler's relation, right? And then like what can you say about its magnitude? 1. Phase? Minus TD omega, right? Correct? Do you agree? Right? So anyway, I need not have even written the imaginary and the real part. I can just observe the exponential function itself. This is just a complex exponential and the exponent doesn't have any real part, right? Pure imaginary exponent, right? So you can immediately get this, right? So what do you think is going to be the shape of this particular sinusoidal transfer function? If I want to plot the real part and the imaginary part, right, what do you think is going to be the shape as omega goes from 0 to infinity? I think this thing should give you the answer. The magnitude is always 1. So what can you say? Circle, right? It's a unit circle, right? Isn't it? The magnitude is always 1, right? And the phase goes like minus TD omega, right? So if you plot it, so I'm just going to try my best to draw a circle freehand. So Let us see, okay. So, how it goes. So, essentially I am going to get a circle, okay, which essentially goes like this, okay. That's aware, this one. This is omega tending to 0. As omega tends to infinity, once again I am going to come back to the same point, right. So, that's what is going to happen to my circle, right. This is the Nyquist plot of this transport lag, okay. Now, let us on top of this, let me superimpose the Bode diagram, sorry, the Nyquist plot of this first order factor, okay. So, let us consider the first order factor. Uh, 1 divided by 1 plus j times t omega, right, which we have already drawn. What was that? That was a semicircle of radius 1 by 2, right, which was centered at, oh sorry, right. So, this is 1 by 2, right, and let us say this is sorry, that is j by 2. So, minus j by 2, this is minus j, this is let me be careful, let me use the same color. So, that this is 1, right, this is minus j, this is minus 1 and this is plus j, right. So, essentially we had a semicircle as the plot of 1 divided by 1 plus tj omega, right, that is what we had, right. Why am I making this comparison? You can see that immediately at low frequencies, you see that the two curves approximately are the same. Do you agree? So, you see that at low frequencies, like the Nyquist plot of e power minus td j omega and 1 divided by 1 plus jt omega are almost the same. Of course, I am assuming, okay, to be very, if I want to be very careful, I should say 1 plus td omega. Oops, sorry. This should be, yeah, okay, because td is the time delay, okay. So, that is what I am doing, right. I make capital T equals td, right. So, at low frequencies, like I am going to have what to say, this thing to be true. So, you can immediately see that for td omega very much less than 1 or omega which is less than 1 by td, you can immediately see that 1 divided by 1 plus j td omega, the magnitude is nothing but, okay, sorry, not the magnitude, the function itself, I can approximate it as 1 minus j times td omega, right, if td omega is very small, okay. Similarly, what can I say about e power minus j td omega? E power minus j td omega can also be approximated as 1 minus j td omega, okay, for low frequencies, right. So, that is what we have, correct. So, you can immediately see that at low frequencies, like the functions become the same. And why did I what to say point this what to say essentially highlight this point here? I told you that like the function e power minus tds is in fact an infinite order factor, right, if you recall our discussion then, right. So, then we had to do some finite order approximations, right, so that we can get proper transfer functions, if you recall, when we want to analyze systems with time delay. What were the couple of approximations that we discussed? One was this, another was the Paddy approximation, right. So, I hope now it is clear why this first order approximation makes sense, right, and it is also very clear when you can apply them. See, suppose if I make this first order approximation, I approximate e power minus tds as 1 minus tds, right. I can use it as long as I am subjecting the system to inputs whose frequencies are much lower than 1 divided by TD. Okay, so that's something which we need to analyze. See, for example, let's say TD is, let's say, like 0.01, then I need to ensure that, like I am essentially subjecting the system to frequencies which are lower than 1 by 0.01, right. So that's something which I need to be careful about. Okay, so then that approximation is very reasonable. Okay, so why am I pointing this? Because we will see that in many engineering systems we may need to approximate time delay, and that is where this discussion helps us, right. It helps us in taking a call as to physically when you can use these approximations. Is it clear? So I just use Nyquist plot to show you that when this approximation is reasonable. Okay, so of course at high frequencies the two curves deviate from one another, as you can clearly observe. Okay, fine. Any questions here? Yeah. Omega tending to 0 where? On the top? Okay, no, omega tending to 0, it starts from down. See, at omega equals 0, it starts from 1 0, it comes into the fourth quadrant. As omega tends to infinity, once again it goes and finishes at 1 comma 0. So for this transport lag, the starting point and the ending point are the same. Which one? No, see, that's where, like, see, you need to essentially use this visualization along with this mathematical plot, okay, because the tan inverse function is also periodic, right. We need to look at it from that perspective. If you plot the, if you keep on plotting the values of the real part and the imaginary part, this is what you will get, okay. So that's where we end up with. Okay, so as far as the Nyquist plot of the transfer function which corresponds to the transport lag or time delay is concerned, it will be a unit circle. Okay, so that's what will happen. Fine. Yeah. Okay, so now I am going to just briefly discuss the second order factor, but I am going to leave it to your homework. Okay, so the detailed plot. So let's go and plot for g of s to be equal to omega n square divided by s square plus 2 zeta omega n s plus omega n square. So this will be 1 divided by, this will, we have already done this when we did the Bode plot. So g of j omega is going to be 1 divided by 1 minus omega squared by omega n squared plus j times 2 zeta omega by omega n, right. So this is something which we already know. So what are we going to get for the real part and the imaginary part? The real part is going to be 1 minus omega squared divided by omega n squared, the whole thing divided by 1 minus, I am just multiplying by the conjugate of the denominator, right. So I am going to get this factor in the denominator, that is the real part, and then I will get minus j times 2 zeta omega by omega n divided by 1 minus omega squared by omega n squared whole square plus 2 zeta omega by omega n whole square. Okay, so that's what we'll get, right. So in terms of magnitude and phase, the same thing I can rewrite it as 1 divided by square root of 1, the real part squared plus the imaginary part squared, right. The real part squared is this, and then the imaginary part squared is 2 zeta omega by omega n whole square, right. And the phase is going to be minus tan inverse of 2 zeta omega by omega n divided by 1 minus omega squared divided by omega n squared. That is going to be the phase. Okay. So this part I am going to leave it to your homework, okay, as to how we got this Nyquist plot for the second order factor. So I am just going to plot the Nyquist plot, like you just need to complete it based on what we have discussed till now. Okay, I just adopt a similar approach. Okay, like just plot sorry, this is not the omega, this is the real part. Okay, this is the imaginary part, and this is the g of S plane. This is the origin. So you will observe that, you know, like all curves are going to start at 1 when omega tends to 0. Okay, and what happens is that the Nyquist plot takes this shape and then like comes like this and ends like this. Okay, so that's what happens for a second order system. Okay, and of course we are going to have a family of Nyquist plots for different values of zeta. Okay, as zeta keeps on increasing, it comes closer and closer. Okay, so this is the trend as zeta increases. Okay, and it cuts the imaginary axis when omega equals omega n, because you can immediately see that at omega equals omega n, right? So you can immediately see that the real part is 0, right? If you look at the real part for any value of zeta at omega equals omega n, the real part is 0. So it cuts, all curves cut the imaginary axis at omega equals omega n. Okay, so this is what happens at omega tends to infinity, but these are the points where omega is equal to omega n. Omega equals omega n is the corner frequency, if you remember, in the Bode plot, right? So what I suggest you to do is essentially construct a similar table as omega tends to 0, omega tends to omega n, omega tends to infinity, and also omega tends to omega r. See, omega r is the point where the, how do you get omega r? Oops. Graphically, I can get omega r. What is omega r? Is the frequency at which the magnitude is the maximum. Magnitude is the maximum means the point should be the farthest from the origin. So for example, here this will be omega r, right? So that's where it is farthest from the origin, right? You get the maximum magnitude. So you can also identify resonant frequency from here, right? So you please look at the resonant frequency also and account for it. Okay, of course, please remember the resonant frequency is reasonable one, holds only for when the damping ratio is between 0 and 1 by root 2. Okay, so this generating this plot, I leave it to you as a homework. Okay, so I have told you the answer. I have also told you the process, right? I have given you the real part, imaginary part, phase, magnitude and all. You just need to construct the table and draw this, right? It just takes this shape. Okay, so then you also need to do the reciprocal. Okay, so that is G. Okay, what is the reciprocal? It's going to be S squared plus 2 zeta omega n s plus omega n squared divided by omega n squared. So this implies that G of j omega is going to be 1 minus omega squared by omega n squared plus j times 2 zeta omega by omega n. Okay, that's the real part and the imaginary part. So the phase, the magnitude and phase is going to be 1 square root of 1 minus omega squared by omega n squared whole square plus 2 zeta omega by omega n whole square. Okay, and the phase is going to be tan inverse of 2 zeta omega by omega n divided by 1 minus omega square divided by omega n square. Okay, so that's what we will get as the phase. Okay, so so once again, if you plot this, you can immediately observe that if you look at the real part and the imaginary part, what can you observe as far as this particular factor is concerned? What can you say about the imaginary part for any zeta? It is always non-negative. See, the imaginary part is plus 2 zeta by 2 zeta omega by omega n, right? So it's always going to be non-negative. What can you say about the real part? it is first going to be positive and then it becomes 0 at omega n, then it becomes negative, but you can see that the real part monotonically becomes more and more negative after that, okay, and the imaginary part becomes more and more positive after that. So you will see that the Nyquist plot of this will look something like this. So this will go like this, okay. So this is what will happen as omega tends to 0, this is what happens as omega tends to infinity. At this point omega is equal to omega n, okay. So I am just giving you the structure of the Nyquist plot, so please complete, okay. Once again, for both these factors, draw the table and then observe, okay. So that's what I want you to do. Is it clear? So you will see that once again, you know, like the Nyquist plot of the factor and its reciprocal, right, doesn't have a correlation as was the case in the Bode plot, okay. So please remember that, that is an important observation here, okay. So this is the Nyquist plot, okay. So I just given you an exposure to introduction to Nyquist plot. So Nyquist plot is also a visualization of the sinusoidal transfer function. So where we plot the real part of g of j omega versus the imaginary part of g of j omega in the complex plane, right. So and important thing to notice is that, like, unlike the Bode plot, I cannot split the transfer function into individual blocks and then draw the individual Nyquist plots and just add them in a very straightforward manner. No, we cannot do that, okay. So essentially I just wanted to expose you to this. What we are going to do tomorrow is that we are going to see how one could use this Nyquist plot to our advantage in stability analysis, okay, which is relevant to this particular course, okay. So I am going to discuss what is called as a Nyquist stability criteria, and we will see how that's going to be used in stability analysis of closed loop systems, right. So that's another technique, okay. So I am just going to discuss that technique with you tomorrow before we go to control design based on frequency response methods, right. So that's going to be the action plan, okay. So we'll meet in the next class and continue this discussion.